So last time we computed if G is SUN, or indeed UN, then the Hilbert space for the two-sphere with two fundamental Wilson lines and two anti-fundamental is equal to C2. And the parameterization is the following. If phi is Cn is the fundamental representation, the basis for the Hilbert space is the identity V tensor V to V tensor V. So it's like EI tensor EJ to EI tensor EJ. And the permutation matrix, which I'm calling rho. So if I draw two parallel Wilson lines, clearly if they don't exchange any gluons, this is just the identity matrix. So classically it's the identity. And if I have two Wilson lines which cross, if I track my states from the bottom to the top, they switch. This is equal to the permutation modulo h bar. So the goal today is to compute the leading order corrections for these statements. So really what we're computing is kind of a scattering process. So what we're going to do, instead of working on the ball, we're going to make the ball very large. So that the boundary of the ball, which is the two-sphere, is at infinity. And then we consider two incoming, two outgoing Wilson lines. And in the three possible configurations. So either they're parallel, this one is over, or this one is under. And what we're going to do is place some states down here and see how they evolve and scatter off each other and what they become at the top. Beginning of Wilson line. What do they become at the end? Okay, so what I want you to imagine is is that this is some version of a kind of standard quantum field theory scattering process. I have states, initial states, they evolve, and then I have final states. The only difference from this and a standard quantum field theory scattering process is that I have these Wilson lines, which that the states are localized at either end. And as they evolve, most of the time they don't get close to each other. When they get, well, you know. So Chern-Simons theory is massless, so there's long distance interactions between them. So when they cross, it's possible for them to exchange gluons, and that changes them, and they go off to something else.
So why do you say there are only 3 possible configurations? What if we like permute twice?
Oh yeah, no, that's true. There are more than 3 possible configurations. I only want to study these 3.
Those will give the leading order corrections?
Well, no, these are Wilson lines. I mean, he was pointing out that there's all kinds of crazy things I could do. I could have crazy knots winding around in the middle. But that's going to be too complicated to really analyze. But so to get this I mean, the Jones polynomial had this property that there was a linear equation about its behavior at a single crossing, and I want to reproduce that. So to do that, I only to study either they cross or they don't cross. So the goal is to reproduce this relation in the Jones polynomial. So the relation was t minus 1 minus t is equal to t to the half minus t to the minus the half. The Jones polynomial has this relation, and I want to reproduce it.
So maybe I'm just a bit confused. So to me, if I cross like this, but then if I go around here, it looks the same as this one. So what? Maybe it's a dimension question.
So how do you mean? Like
they're not actually touching when they cross. Right?
No.
So how close are they in the transverse direction or into the board? Or does that matter?
They're at some finite distance. Say h. And here the distance is h, and here the distance is minus h.
Okay, and what about the first one?
They can be at the same, it actually doesn't matter.
Okay.
We get the same, I mean, it turns out that this one, well, I'll write down the Feynman diagram we're going to compute, and the answer for this one is nothing. So this one, if I try to exchange gluons, this does not contribute anything. So it doesn't actually matter. So we'll compute the leading order correction. Order h bar. So recall the propagator say for the U1 case is P, this is up to some normalization, which I'm always getting wrong. IJK, xi minus yi, dxj minus yj, dxk minus yk over x minus y, 3 over 2. Those are 3. Well, the propagator for the GLN case is going to be the same, but I'm going to decorate it by some flavor index. For UN or GLN, it's a little easier to use GLN. the same, but decorated by a flavor index. Let's call this E is the same thing. Times sum of EI AB tensor EA. So what is E? EAB is the n by n matrix with 1 in the AAB entry and 0 elsewhere. So is this a familiar expression for the propagator of a GLAN gauge theory? Maybe I should remind you, like, the reason this comes about is we have, if I just analyze the color indices in the kinetic term, arises because the kinetic term has trace A dA, and if I can diagonalize the trace pairing on GLN by using these matrices. And trace EAB, EKL is delta AL, delta KB. So, as always, I look at the flavor factor. I find some expression on the Lie algebra, which I have to invert, and this expression inverts it. Sorry, I'm not being very clear here, but I hope this is reasonably familiar. Yeah?
So distance is defined, I mean, what's the definition of distance in the gauge group?
What's the definition of which, sorry?
Distance, I mean the dx.
I'm not sure I understand. I mean, this is a, so if the case is a U1, this is a 1 form. This is like a 2 form in or 3 times or 3.
Oh, it's D, oh, sorry. Yeah.
So this is like the,
Yeah, it's relative, sorry.
so if I'm going to study the crossing, I'm going to integrate x over one line and y over the other line. So if we study the exchange of one gluon, we have I take my initial states, so there's going to be two factors for how, for what happens. There's going to be something where the color indices of the propagator hit these states, and then there's going to be an integral. This gives final states. Well, this guy is coupled with some E or S tensor E, S, or, so I'm going to hit these matrices with these states. So we get color factor. Wow. as this one goes along, it hits this matrix, ES OR. So that will be ES OR EB. And this one will get E or S EA, which is because this matrix is 1 and only one entry, this expression here is delta SB. That's delta SB E or tensor delta A or ES, which is what it is. It's something pretty simple. I'm sorry. See, so what are the possibilities? So if we get this right, this is equal to I'm being really dumb. So this index OR is A. So I've this EA. That's EB. Okay. So what have we determined? So the color factor at order h bar for this diagram sends EA tensor EB to EB tensor EA. So to EA tensor EB. So it is the identity. Okay. Is this making sense to you guys? No.
I'm a bit lost. I'm sorry, I don't know if is that I don't remember anything from QFT, but yeah, I didn't understand anything of the computation of that diagram.
Well, I didn't compute the integral, you see. So there's some number attached to it, which is going to be given by an integral. I didn't do that. All I did was like study what the matrices were. So let me draw another picture.
Maybe, for example, would help if I understand what the interaction vertex is. So what it means for Wilson lines to exchange gluons.
Yes. Okay. Let me draw them as if they're parallel or something. Here is my gluon, and the color factor for my gluon is a matrix at each side. So this is sum E or S here and ES or here. That's because these are an orthogonal basis for the trace pairing on GLN, and the trace pairing was what I used to define the kinetic term. Would it be more transparent if I used a different basis, if I used the basis of Pauli matrices? Is that more familiar to you?
I don't think that necessarily is the problem, but So in my head, we have this action, which has the Chern-Simons part.
Yes.
Which the ADA term, we obtain that propagator.
Yes.
We have a cubic term in that action that is going to give me some interaction between. It's going to give me a triple gluon vertex.
Right, which we're not actually using. That will appear in the next order.
Pretty high order, and then I imagine that this vertices between our Wilson lines and the gluons are
Yes.
coming from the integral, from the Wilson line term in the action, right?
Yes. Sorry, there's two ways to think about that. The Wilson line is a path-ordered exponential. So let me draw. So if I take general Wilson lines, the Wilson line is a path-ordered exponential. So I have a bunch of points, an arbitrary number, each of which is coupled to the gauge field. Right? Because it's the integral over some number of points in increasing order along the Wilson line. That was the definition of the path-ordered exponential.
And it appears something like gamma, well, a mu and the curve mu, right?
Yes.
It appears in blocks like that in the path-ordered.
Yes, I take my one form and I restrict it to the curve. And now, what's the general Feynman diagram? I just couple these guys up, and I'm also allowed to use bulk interactions. Okay? So that's one way to think about it. But this will be an expression of very high order because each propagator contributes a power of h bar. So if I want something only to leading order, I only care about the leading term in the Wilson line, which is where there's a single point, and I'm integrating this guy over this line and this point over this line.
Can we write down that term of the? I'm sorry. Is this trivial for everyone? I don't know.
No, I think everybody's confused. So what I wanted to do was separate it into something really stupid and easy, which is the color factor, and it's something interesting and difficult, which is the thing you're interested in, the integral.
But just like my last, can we write down that term in the action, the action of the...
Yeah, so it's just the integral along the Wilson line, which is an open Wilson line, of the OR S matrix entry coupled to this matrix ES OR. So this guy acts on a state at the end. So it's slightly tricky because it's an open Wilson line and I'm acting on a state. Perhaps the better way to think about it is, why is the Hilbert space for a Wilson line Cn? The reason is a Wilson line is just coupling quantum mechanics. The Hamiltonian of the quantum mechanics is my gauge field. So if my gauge field has the matrix OR S in it, it means that will appear in the Hamiltonian. So a state will evolve by hitting it with that matrix.
Yeah, I think that there's something that are sources of a lot of confusion. So maybe is that now if I understand what you're saying is that this line is having on a field theory on R.
Yes.
This diagram is on
it's a couple
on the line.
Well, there's a couple system. There's one field theory on the line whose Hilbert space is C to the n, and where the states evolve, the way they evolve is given by the gauge field. Now there's another one over here where they also evolve given by the gauge field. And the muon exchange means these two systems have a kind of an entangled Hamiltonian.
Okay, I get it. So you were computing some expectation value, and you had the exponential of the interaction Hamiltonian, precisely bringing down that h bar is bringing down one of those integrals.
Yes. So maybe I should write that out a little. So I realize this is kind of obviously very tricky. Okay, so this line has Hilbert space c to the n. Let me just draw them. I'm going to draw them both on axes. So this guy is at height 0 and the vertical axis. And this one is also, let's say, height h and horizontal. So the propagator means that the two quantum mechanical systems get coupled by a Hamiltonian which is sum so this is the color factor of the Hamiltonian, and there's some coefficient which depends on the points.
I mean, isn't the coefficient precisely A?
The coefficient is the propagator.
Yeah.
What? There's no tables.
What's that? What's that? No time?
No, I was just confused where the E lived. And I just, sorry.
Oh, these are just
Yeah.
elementary matrices. Well, so if I take that expression and I restrict x to one line and y to the other line, what do I get? Up to an overall factor, I'll get h, which is y3 minus x3. Since x2, since one of them is always at the origin there and the other is always at the origin center axis, oh, it's all y1 is 0 and x2 is 0. So I'll get h dx1 dy2 over h squared minus y1 squared by 2 squared times 3 over 2. Does that make sense? So all I've done was substituted where we substitute, we restrict x3 equals h, y3 equals 0, x2 equals 0, y1 equals 0, to place ourselves on these two lines. So y2, so that the y coordinates on one line and the x coordinates on the other. So is this making any more sense?
A bit more.
A bit more, okay. So I think you wouldn't, if this was a U1 gauge field, I think you wouldn't be worried at all, right? Because then you wouldn't have this matrix here, and all I would be doing was taking the propagator and putting one leg on one line and the other on the other line and integrating. Would you agree? I mean, this is the same thing we did when you computed the linking number.
You have to worry about Gluon polarization.
What does that mean?
Well, you usually have these extra polarization factors when you compute Gluon exchange defining diagrams. You don't seem to have it here. So.
Is that like something only in Lorentzian signature, or?
Oh, maybe. Yeah, probably.
What do they look like? Is it?
Epsilon mu or epsilon mu?
Oh, yes. No, that's the. So it's some epsilon in the spacetime indices.
Yeah.
So probably there's two things going on. Firstly, because Chern-Simons theory has a different kind of kinetic term than Yang-Mills theory, and also I'm using form notation, so there's some anti-symmetry. So. Okay, so if everybody's reasonably happy, so we can ask. Oh, actually, there was one more thing. Say, why did I not find a DH? And the important thing is H is constant on the lines. Since H is constant, no DH can appear. Go over here. Okay, so this is what happens when the lines cross orthogonally like that. What happens if they're parallel? So if they're parallel, then say x2 minus y2 and x3 minus y3 are constant. Only the difference in one thing varies, because no matter what 2 points on the line I have, their difference in this direction and in the plane orthogonal to the blackboard is just the same no matter where they are. Only their vertical distance can vary as they're varying my points, but the distance in the other two directions can't. So this means, well, because these are constant, dx2 minus y2 is 0, and dx3 minus y3 is equal to 0, implies the propagator is 0. Because in xi minus yi dxj minus yk, yj dxk minus yk, epsilon ijk, there will always be one of those or one of those. Okay. So now, to figure out.
Sorry.
Yeah.
That's a good question.
Uh-huh.
If I remember correctly from last lecture,
Yeah.
how do it have to do with the parallel transport?
Exactly, yes.
Like, I understand when we just have one line, but how are you solving that differential equation when you have like those two lines? I just can't picture what, like, how are those?
Yeah, good question. So, well, when I said that that they were kind of coupled, it's a little misleading, right? Because this x1 coordinate is the position along here, and the other is the position along here. And the Hamiltonian depends on both positions. So, how would this work? I mean, what I'm going to do is just integrate this over here and here. So I think you will end up with something which satisfies a second-order differential equation. Because if I integrate this propagator over here and here, if I differentiate with once with respect to this variable, I will get its value here. And then I have to differentiate it with respect to the other variable. So I haven't really thought about this, but I think the kind of Hamiltonian thing you'll get will be d by dx, d by dy is the time-dependent Hamiltonian. Does that make sense?
I'm just bothered about that trace pairing. Like I can't see how it's rising from the
from the kinetic term.
Yeah, so like even for that differential equation for the because you're saying that's the Hamiltonian. Like it doesn't seem natural to me that you have that trace pairing. Like because I imagine that line feels, I don't know, somehow independent from the other lines.
I see what you're saying. I think I didn't, like when I said this is Hamiltonian, it's not. Here's another way you might proceed to understand it better. Is works better in the case of U1, but if I fix one line, then I can solve the equations of motion in the presence of that line.
Yeah.
And I get some gauge field. That gauge field I view as a Hamiltonian for the other line.
That gauge field, sorry, what happened to the other line?
So I solve the equations of motion in the presence of this line. I get, at order h bar, I get some gauge field which has some kind of singularities on this line. And it's closely related to the propagator. Now, that gauge field, I see what it does to the other one. I view it as a Hamiltonian for the other line.
Oh.
So it's a little bit asymmetric. So maybe the discussion of Hamiltonians is a little misleading and we should just believe the Feynman rules? I don't know. Is that unsatisfying?
Why the trace pairing again?
Well, the trace pairing is because in the kinetic term I have trace ADA. And if I expand A into elementary matrices, this becomes the sum of A or S, dA, S or. So the kinetic term has the same kind of form as this propagator. One. So now to figure out what happens to a state at the end and what it evolves to, we just have to compute this integral.
One more question.
Yeah.
A T is action. What kind of TFT is this again?
It's a TFT with codimension 2 defects. So I get a Hilbert space for a manifold with points in it, and a linear operator for Hilbert space for a surface with points, codimension 2, and then linear operators for 3 manifolds with lines in them. So there's a whole zoo of like TFTs with defects of various dimension that give you all kinds of variants of the axioms. Oh, and if you're in Lurie's paper, it's called the tangle hypothesis, this kind of thing. In any case, so how do we do this integral? So if I take initial states, say EA, EB gets sent to something like this. We switch them just because of the way we view them. This is BA. This is the reason that these are switched is some kind of convention. So we get this time times the double integral for x, y of h dx dy over h squared plus x squared plus y squared 3 over 2. So let's compute this integral. I'm not actually going to compute it, I'm just going to show it's non-zero and understand its dependence on h. So if we let, say, x tilde be x over h, then 1 over h squared plus x squared plus y squared 3 over 2 is equal to 1 over absolute value of h, 3 over 2. So 3, sorry. Okay. So similarly, x tilde and similarly, sorry, y tilde, need something very trivial here. Similarly, dx dy becomes h squared dx tilde dy tilde. So we get the integral x tilde y tilde dx tilde dy tilde over 1 plus x squared plus y squared 3 over 2. And now is the absolutely crucial part. The factors of h almost cancel out. Don't. What we're left with is the sign of h. Because on the top, we have h squared and h cubed. And on the bottom, we have the absolute value of h cubed. So we get different values if h is positive or negative. This whole thing here is equal to the sign of h. And this whole thing here, well, this is positive. So I'm integrating some positive number over the plane. So this is some number. Some positive number. So the answer is the sign of h times some positive number. In other words, if I do my lines in the other order, I get a different sign. So in sum, absorbing the value of the integral into the normalization of h bar, h bar, we find that this crossing sends EA tensor EB to EB tensor EA plus H bar E or S EB tensor ES or EA, which is EB tensor EA plus H bar EA tensor EB. Whereas the other crossing has a different sign. EB gets sent to EB tensor EA minus H bar EA tensor EB. Okay, so that went reasonably fast, but is that, I mean, the details of the integral don't matter, only the fact that you pick up a sign, that's the only important thing. So now we can see the sign relation of the Jones polynomial. We'll find something tiny little bit different because we're using UN instead of SUN, and there's some extra factors from SUN, but the difference is really minor. So if rho is equal to the flip, what we find is L plus, which is this gives me rho plus H bar times the identity, L minus gives me rho minus H bar times the identity, and L0, which is the parallel lines, gives me the identity, all this modulo H bar squared. And if you recall, these two matrices were a basis of the Hilbert space. So they were basis for all possible scattering processes. So we have this relation, this minus this is equal to this times 2 H bar. So if we compare, we have as you can see, this is very close. Okay, any questions about this relation?
Additional question: is there any reason you call those operator L mod? Those are the same operator in CFD.
No, I'm just, this is what Jones called these three crossings. I don't know why. Something from knot theory, I think. So these will be particularly close if you say a T looks like e to the 2 H bar, and this thing will look like 2 H bar plus order H bar squared. To get these factors right, we have to modify the color factor a little bit. So if we modify, use SLN rather than GLN, so the color factors are modified a little bit. You gave, well, I think, so this is some small little calculation with writing down the color factors for SLN. This guy will be rho plus h bar times the identity minus h bar over n rho. Rho minus h bar times the identity plus h bar over n rho. So we get L plus minus L minus is equal to 2h bar L0 plus h bar over n rho. And since modulo h bar squared, these guys are both equal to rho, L plus 1 plus h bar over n minus L minus 1 minus h bar over n is equal to 2h bar 0. And if you proceed in this way, you get something which is rather closer to what Jones wrote. I'm afraid I've got some factors wrong, but you can certainly imagine fiddling around with it and producing exactly that relation. Modulo h bar squared. Okay, any questions? Everything is crystal clear? No? I didn't think so.